So now we'll talk some more about equivalence classes, and we'll cover three theorems about equivalence classes. We're not going to go through the proofs because they rely on techniques that we haven't learned that would be covered in chapter 11, which we had to skip. But if you want to see the proofs for yourself, I would encourage you to read the book. It explains it pretty well, though you might need to read chapter 11 beforehand to fully understand the proofs. Anyways, we don't need to understand the proofs. I'm just going to give you the theorems and examples. So first theorem, suppose we have an equivalence relation R on a set A. Suppose also that A and B are elements of the set A, right? So you have little a and little b. Those are elements of set A. Okay, so that's our setup. Now here's what the theorem says. The theorem tells us that the equivalence class of A is equal to the equivalence class of B if and only if A is related to B. So let's recall, if and only if means it goes in both directions. So what does that mean? That means if the equivalence class of A is equal to the equivalence class of B, then A must be related to B. And conversely, if A is related to B, then the equivalence class of A must be related to B, right? So both of those things are included in the if and only if. That's the meaning of if and only if. So for example, consider again the equivalence relation congruence mod 3. Congruence mod 3, okay? So this is telling us, I should have said it's a relation on the set of integers, but right, that's the same relation that we've been talking about for a while. So it's an equivalence relation on the set of integers. It tells you whether one integer is congruent to another integer mod 3. So consider this equivalence relation. Now for this relation, we said that the equivalence class of 0 is this, and we also noticed that this set is also the equivalence class of 6 and also the equivalence class of -6 and so on and so on. So here we have two equivalence classes that are equal to each other, right? We have the equivalence class of 0 that is equal to the equivalence class of 6. So that's our equivalence class of A is equal to the equivalence class of B. So the theorem tells us that because the equivalence class of 0 is equal to the equivalence class of 6, therefore 0 should be related to 6, meaning 0 should be congruent to 6 mod 3. And that is in fact true. Now, conversely, we can do the other way as well. We know that, well, you should check out, but it is a fact that 2 is congruent to 11 mod 3. Okay, so verify that, but it is a fact that 2 is congruent to 11 mod 3. So the theorem predicts, so because A is related to B, right, 2 is congruent to 11 mod 3, the theorem predicts that the equivalence class of A should be equal to the equivalence class of B. So the theorem predicts that the equivalence class of 2 is equal to the equivalence class of 11, which is also true. All right, now before we introduce the next two theorems, we have to have a new definition, and that is partition. So it's a long definition, it has multiple parts. So we'll try to go through it slowly and give examples. So a partition of a set A. Okay, so we start with a set A and we want to partition it. So first, the intuitive idea of a partition is just dividing it up into a bunch of smaller parts. That's all, right? Taking a set and dividing it up into a bunch of smaller parts. But we want to be very precise about our definitions, and that's generally the thing we do in math. We don't just give a vague definition; we give a precise definition that covers all possibilities, that we're interested in. So this is, a good thing to be able to do in general, to be able to give precise definitions. So we're going to do it precisely. So a partition of a set A is a set of non-empty subsets of A. So if you take a set and you partition it, you divide it up, you end up with a bunch of subsets, right? A bunch of subsets of A. And we're going to say that each of them cannot be empty. They have to be non-empty, such that the union of all the subsets is A. Again, if you take all these little parts that we partition A into, and you union them together, you should end up with A. All right, so if you take all those little parts and you put them all together, you should end up with A. And also the intersection of any two different subsets is the empty set. Right, so there cannot be overlap between different parts of the partition. When you partition a set into a bunch of smaller parts, they have to be distinct. Each part has to be separate from each other part. There cannot be overlap between two different parts. Let's see some examples. So if we have a set A equal 1, 2, 3, 4. So here is a partition of A. It's a set of non-empty subsets of A. Right, so these are all subsets of A. They're not empty. Each of them is not empty. And the union of all these subsets, so if I take all these together, I end up with A. And there is no overlap among any of them, right? So the intersection of any two different subsets is the empty set. There is no overlap. If I look at each of these sets, there's no overlap among them. So this is a partition of A. How about this? Is this a partition of A? Yes, it's another partition of A. So in general, a set has many different partitions, right? Many different ways of partitioning it. How about this? Is this a partition of A? Okay, hold on, I'm missing a curly brace there. All right, so it's fixed. Is this now a partition of A? So it's not, because the definition says that a partition of a set A is a set of non-empty subsets of A. But here, one of these subsets is the empty set. So it's not a partition of A. How about this? Is this a partition of A? So there's no, these are all subsets of A, and there's no empty set in them. Here's another problem, though. We need to make sure that the union of all the subsets is A. But what's the union of all these subsets? It's not A, because we're missing 3. We're missing the number 3. So this is not a partition of A. How about this? So here, the union is A. The union of 1, 3, 2, 3, 4. If I put them all together, that's A. So that's good. But here we have another problem. We need to make sure that the intersection is of any two different subsets is the empty set. In other words, we need to make sure there is no overlap among these subsets. But if we look at this first subset and this last subset, there is overlap. So this is also not a partition of A. How about this? Is this a partition of A? So this is a set, and it has only one subset of A, and just A itself. So is this a partition of A? I would say yes. I would say it fits the definition. It's a set of non-empty subsets of A, right? So each of the elements of this big set is a non-empty subset of A. If I take this, well, I have nothing to union it with, but it's just, the result is just this set itself. The intersection of any two different subsets is the empty set. Well, there is only one subset here that I'm dealing with. So obviously there is not going to be any overlap with anything else, because there's only one subset in total. Anyways, I think this is a partition. This is a partition of A. Okay. All right. So now that we have this new definition, let's show the connection between equivalence relations and partitions. Okay. So the next two theorems are going to show the very tight connection between equivalence relations and partitions. So the first theorem is as follows. Suppose R is an equivalence relation on set A. Then the theorem says as follows. The equivalence classes of R form a partition of A. All right, so remember, when we have an equivalence relation, we can form the equivalence classes, right? Based on the equivalence relation, we have equivalence classes. And this theorem says that it will always be true that the equivalence classes of R will form a partition of the set A. So let's see an example of that. Again, we're not seeing the proof, but the proof is in the book. And it's a nice proof, but we're not going to look at it. So sorry, here, let me just restate it. So in other words, the set of all the equivalence classes, right? So the set of each equivalence class of A, where A is an element of the set A, that is a partition of set A. So for example, consider again the equivalence relation congruence mod 3. And this is a relation on the set of integers. it tells you whether one integer is congruent to another integer mod 3. So we found the equivalence classes of this relation, right? In the last video, we found the equivalence classes of this relation are the following. We have 3 equivalence classes. Equivalence class of 0, which is this, equivalence class of 1, which is this, equivalence class of 2, which is this. And we found that these are the only 3 actual equivalence classes. So the following is a partition of Z, meaning I could take all these equivalence classes, right? The equivalence classes of R will form a partition of A. So the following is a partition of Z. In this case, our set is Z. So in other words, we take each of these equivalence classes, and they are the subsets that are in the partition. So this partition has 3 parts, 3 sections, whatever you want to call them, and they are the equivalence classes of R. So the equivalence classes of R, or sorry, the equivalence classes of this relation form a partition of Z. Or more compactly, the following is a partition of Z. The equivalence class of 0, comma the equivalence class of 1, comma the equivalence class of 2, right? So that's exactly the same thing as this line, just in a much more compact form. So notice, and this is very reasonable, right? So every integer is part of one of these 3 subsets, right? Every integer is either in here, or in here, or in here. Of course, you can't see it because I didn't list them all out because there's an infinite number of them. But there are only 3 categories. Each integer falls into one of these 3 categories. And these are the equivalence classes, which also form a partition of Z. Okay, so this is again based on the theorem that says that the equivalence classes of a relation form a partition of the set that the relation is on. Okay, so what do we see in this theorem? We saw in this theorem that if you have an equivalence relation, you can form a partition. Again, suppose you have an equivalence relation, then you have equivalence classes, and the equivalence classes form a partition. Right? So you start with an equivalence relation, and you can get from there to form a partition of the set. So that's this theorem. The next theorem tells you that you can go the other way as well. So the next theorem says if you start with a partition, you can form an equivalence relation. So suppose P is a partition of a set A. Consider the relation defined by X being related to R if and only if X and Y are both elements of the same subset X for some S that is an element of P. So P, again, is a partition, meaning it's made up of a bunch of subsets of A. So you can make up a relation as follows. You can say that X is related to Y if and only if X and Y are both part of the same subset. Okay, so we start with a partition and then we make up a relation. So the theorem says as follows. It says it will always be the case that R is an equivalence relation, meaning this relation R that we made up here will always be an equivalence relation. So again, this theorem says if you start with a partition, you can form an equivalence relation. The previous theorem, what did it say? The previous theorem said if you start with an equivalence relation, you can generate a partition. Okay, but so this is the other way around. So for example, so let's say we have a set A as follows, and suppose we make the following partition of A. So we'll call it P, let's say, and the partition is made up of 3 subsets. This is one, this is another subset of A, and this is a third subset of A. Right, so this is a partition. It's made up of 3 subsets of A. Now, consider the relation R on A defined by saying that X should be related to Y if and only if X and Y are part of the same subset, right? So if they're part of the same sort of block here, okay? And so for example, 1 would be related to 1 because they're part of the same subset here. 1 would also be related to 2 because they're part of the same subset here. 3 would be related to 3 because they're part of the same subset. But 3 would not be related to 2, right? 3 would not be related to 2 because they're in different subsets of the partition, and so on, right? So suppose we make up this relation. the theorem predicts that R will always be an equivalence relation. And in fact, it is.